I got 13 out of my 50 to land upright. Does everybody have their point estimate? After you've got your point estimate, please go ahead and zip up your little Ziploc baggie and I will recollect those. I know, I wish we could eat them. There's a lot of M&Ms though. Or not. People say M&Ms, but Hershey Kisses. Hershey Kisses. I don't know why I keep having trouble with this today. Thank you. Thank you. While I'm collecting these, I want you guys to answer number 2. What is the population? What is the parameter? What is the sample? What is the statistic? Try to answer number 2. Thank you, ma'am. What is our population? All Hershey Kisses. What is our parameter then? True proportion of Hershey Kisses that land flat. What should we use to designate the parameter? P. So our parameter P is the true proportion of kisses that land flat. What's our sample? 50 Hershey's Kisses. And what is our statistic? P hat. Do we have a value for P hat? Is everybody's value the same? No. My P hat came out to be 0.26. You need to put whatever your P hat was here. Question number 3. Was the sample a random sample? Yes. We randomly sampled 50 Hershey Kisses. Why is that important? That it's a random sample. What can we do with it because it is a random sample? Why does it matter that it's random?
Put it to the population.
Yes, we want to generalize this out to the population. when we are talking about estimating a population proportion, which is what we're doing right here, estimating a population proportion, this is the first condition that we have to meet. Condition number 1, it has to be a random sample. What is the formula that we would use for calculating the standard deviation of the sampling distribution of p hat? If you need to pull out your formula sheet, you may do so. What is the formula for calculating the standard deviation of the sampling distribution, the standard deviation of p hat? Square root. Since we're talking standard deviation, we've always got square roots in here. Over n. Now question, do we know p? No, since we don't know p, I can't use p here, but what could I use instead? I can use p hat. I can use my estimate. So p hat, 1 minus p hat. Here, I'm going to leave this one right here with just the p's because this is calculating the standard deviation. Number 6, we don't know the value of p. So we will use p hat. I skipped number 5 because I kind of got ahead of myself. What condition must be met in order for me to be allowed to use this formula or its variation? 10% condition. Has that been met here? How do you show it? How do we prove that that's been met here? Yes. Because remember, 10% condition says n is less than or equal to 1/10 of my whole population. So 50 is less than or equal to 1/10 of all the Hershey Kisses. So we're saying there's at least how many Hershey Kisses? 500. Do you think 500 is less than or equal to all Hershey Kisses? Yes. I think we probably had 500 just in the room or close to it. So I'm going to give myself a little check mark here and point to this to say the 10% condition has been met. This is condition number 2 that we always have to check for. So far we're talking about other things that we've had to check for in the past. These are all integral parts of us estimating the true population proportion. So we have to check to make sure that we have a random sample so that we can generalize to the whole population. We have to check to make sure that our 10% condition has been met, because we need to know that sampling without replacement is not changing things, that this is still independent. This guy right here, since I'm using p hat, this is actually the standard error of p hat. So instead of writing sigma p hat, we're going to write SE p hat. This means the standard error of p hat. I want to go ahead and calculate everybody's going to have a different one. I want you to calculate what your standard error would be using your p hat. So for mine, my p hat was 0.26, and then I do 1 minus 0.26 over my sample size of 50. Everybody should have a different standard error. I don't like that one. I got 0.062. Did anybody else get numbers similar to that? All right. I'm going to make sure that we have our standard error formula. Standard error for p hat is the square root of p hat times 1 minus p hat over n. Almost exactly the same as standard deviation, except I'm using p hat instead of p, so it's not standard deviation, it's standard error. You guys okay with that difference in wording because we're using p hat instead of p? All right, let me see if it'll let me grab all of this now. Last condition that needs to be met. Make sure everything fits on my screen here. Would it be appropriate to use a normal distribution? Why or why not? Large counts, so we have to check that. We have to check our large counts condition. How do I check my large counts? So n times p, but do I have p? So I'm going to have to use what? So n times p hat and n times 1 minus p hat. And we need both of these to be bigger than what? Greater than or equal to 10. Check that yours meets the large counts condition. So on mine, I have 50 times 0.26. $13 greater than or equal to 10, so we met it there. So yes, it is approximately normal. This is condition number 3 that we have to check for. So there are 3 conditions that we have to check in order to be able to estimate a population proportion. We have to check to make sure we have randomly sampled. We have to check our 10% condition so that we know it is independent. We have to check our large counts condition so that we know it is approximately normal. In a normal distribution, let's see who remembers this. In a normal distribution, 95% of the data lies within how many standard deviations of the mean? 2. actually not exactly 2. It's approximately 2. But that's what we learned with our empirical rule. We had the 68, 95, 99.7 rule, and it's approximately 2 standard deviations. I want to figure out 80% of our data lies within blank standard deviations of the mean. 90% lies within, we know it's close to 2. We're going to calculate a little bit more precisely. I want you to go ahead and grab your calculators out for me. We're going to use inverse normal here. Now, whether I'm using table A or the calculator, I want to be careful, because if I have 80% right here, I want to figure out how many standard deviations I would be. If I'm using table A and I'm trying to find this value right here, table A goes all the way over, right? So what are the percentages in these two tails? If 80% is in the middle right there, 10% on each side, because altogether that would add up to what? 100%. So I want the area that's 0.90 if I'm using my table A or I'm using my calculator. So I want you to grab your calculators. We're going to do inverse normal. .90. Grab your calculators and do that, and tell me what you get. 1.28. Take it out to 3 decimal places for me. You said 1.28, and I didn't hear that last number. 1.282. That's my critical value, that 10% tails on either side. We call this a critical value here. Just for giggles, put in inverse normal of 0.10. Negative 1.282. So that's telling me 1.282 standard deviations just to the left. So same critical value here. I'm just going to ignore the negative. My critical value is 1.282. That is 80% of the data lies within or between 1.282 to the left, 1.282 to the right. So I'm doing inverse normal of the tail. Let's find what our tail proportion would be for 90%. What would my tail proportion be if I wanted to capture 90%? How much would be on the sides? 5%. So do inverse normal of 5%. Inverse normal of 0.05. What are we getting? So you got negative 1.645. So my critical value is going to be within 1.645 standard deviations to the left or to the right. 95% of the data. How big is my tail? 2.5%, right? Because I have 95% in here. So my tails are each 2.5% to add up to 100%. So I'm going to do inverse normal of the table, inverse normal of the tail. So inverse normal of 0.025. You said 1.96. And then it's just got a 0 after that, right? So 1.96, even if we round it. So within 1.96 standard deviations, 99%, how big would my tail pieces be? 0.05. If I want 99% here, I have 0.05% in each of my tails. So I'm going to do inverse normal of, what do I type in if I want 0.05%? 0.0005. Did I have too many zeros? Yes, thank you. I've got one too many zeros because I wrote it wrong. 0.5%. There we go. I wrote one too many zeros there. I apologize. 0.5% in each of my tails, so 0.005. What do we get? 2.576, yes. That one technically came with a negative in front of it, right? But that's just telling me to the left. To the right, it would be 2.576 standard deviations. These are called our critical values. And these will be very important as we move forward. So we're going to calculate the margin of error for a 95% interval. Do you guys remember the other day when we were just making guesses at what our margin of error should be and we were adding and subtracting that to both sides? If I want to say I am 95% confident or I am 99% confident, we take the critical value for a 95% interval and we multiply it by the standard error that we found. Good grief. Standard deviation or standard error. So you might need to flip back on the front side to see what your calculated standard error was. Mine was 0.062. I'm going to multiply that by the critical value for the 95% confidence interval. What was the critical value for 95%? 1.96. So I'm going to multiply those together. I got 0.1215. Yours should be different than mine, although it should not be horribly far away, but yours should be different than mine. What in the world? Okay. Let me grab all of that. Now I want to take that margin of error and I want to use it to find a point, the confidence interval. So point estimate plus or minus the margin of error. My point estimate that I found when I did my kisses, I had 0.26. You'll need to look back to see what your point estimate was. Plus or minus the margin of error that you just calculated in number 9. So I'm going to add and subtract that to 0.26 to come up with my interval. So mine is approximately 0.14 to 0.38 if I'm just looking out to 2 decimal places on mine. Find your interval, and we are going to add it to a graph that I'm going to put up on the board. Everybody's going to come up here and draw their interval. So mine is from 0.14 to 0.38. So 0.14 would be about here. Come on. Why are you being difficult? 0.14 to 0.38. Once you have your interval, please come up and add it. We're going to go kind of down, similar to that app that we used yesterday where it showed all the different intervals. Perfect, thank you. Right there, we're going to take and multiply by your critical value. 0.7 by that right there. So this is what I got. Yes, so let's do that. So you had more than half of yours like that, right? Okay, so we're going to take 1.4 minus that, 0.402, 54 plus that, 0.6. So that's what you're going to go from and plot. So from about 0.4 to about 0.68. Okay, you're welcome. After you have drawn your interval up here, I want you guys to copy this into your notes so that you have it to look at. My drawers come down. See if there's room towards the bottom or in between some of the ones that have been made. Let's see, yeah, if you can fit yours in between, perfect. I want you guys to copy this into your notes so that you have it to look at. But I want to use this now to see if we can estimate what we think the true population proportion is. Let's see if I can get rid of this little guy here. Oh, nope, I cannot. It's got the whole thing there. Where could I draw a vertical line that would capture almost all of these intervals? 0.4, if I draw out 0.4, that hits all but like 2 of our intervals. Absolutely. I think that's probably about right. 0.39, 0.4, somewhere right around in there, depending on how accurate we were. So what do you think is the true proportion of kisses that land flat? We're making our estimate for P. I like using 0.4. If you wanted to put 0.39, that would be fine. But the idea is that we want to be capturing almost all of these intervals. Let's see, we've got 19 people, including me. Because of the number of people that we have in the room, we missed how many intervals when we drew it at 0.4? We missed 2 intervals. That puts us at 0.89 of the intervals that we drew. Very close to that 95%. So we are 95% confident that the true population proportion is captured by, we are 95%, approximately 95% of our confidence intervals capture the true population proportion. I want to get our big ideas written down for today, and then we'll do the check your understanding at the beginning of class tomorrow. I do also want to get your 8.2 homework passed out to you so that I do not forget. 8.2 homework is due on Monday. Today is when the 8.1 homework is due. We covered all of that material the last 2 days, so we're all the way through 8.1. 8.2 is today and tomorrow's material, and it is due on Monday. 8.3 is very, very short. We will cover 8.3 on Monday, and that finishes up our chapter 8. Let me get the big ideas up here, and I'll be right there. Important ideas for today. We have to check our conditions. That is the first most important thing. We have to check that our conditions are met. Our conditions are randomness, 10%, and is it normal, which we're going to use our large counts condition for. Important critical values. We call these Z-star values. And then we have a general formula for a confidence interval. That's our point estimate plus or minus the margin of error. That is always how we will calculate a confidence interval. For a proportion that is specifically going to be p hat plus or minus z star that goes with whichever confidence level we're looking at, times the standard error of p hat.